Hello, everybody. Welcome to Discrete Mathematics for Computing. You know me by now, right? So welcome to class. This is what I have in store for you today. We're going to talk about the empirical rule. Now, I know you're looking at the slide and you're like, well, Bob, it says the empirical rule and z-score probability. We're going to talk a little bit more about z-score probability in the next lecture. It's important for me to break this down into two lectures because there needs to be a time interval between the empirical rule and z-scoring if you're just learning this. Disclaimer, math alert. This stuff is very dense. You know what that means? That means that it's not light reading. I only have 3 slides for you. If you're just learning this, you're going to be staring at these slides for the next hour. Well, maybe not, as I'm doing it, but, when you're going over this for yourself, you're going to stop and just stare, connect the dots. There's a lot of numbers. There's a lot of intervals. There's a lot of percentages. This is not something that you look at and you go, yeah, I get it. Yeah, okay, go on to the next one. No. You need to stop and you need to really think about what you're looking at. So don't try to do this quickly if you're just learning this. If you're getting a refresher on this, you know what I'm talking about, and then you could probably go a little bit quicker through it. I'm just trying to give you guys some steps for success here in learning this stuff. This is not real quick, easy breezy. Let me read this and just say, okay, that's right, 1492, and remember the dates and memorize this because it doesn't work like this. This has to deal with developing critical thinking and absorbing some very deep concepts. I didn't say this was hard. I said this is dense and it's very deep. So let's talk about the empirical rule. Now, what we've done so far in class is we've done things such as look at descriptive math, right? Remember, descriptive math or descriptive modeling or descriptive data modeling or discrete data modeling, all kind of same words for the same or similar words for the same thing, has to do with using math to observe and measure the world around us. That's not a definition. It sounds like I'm on Wikipedia again. I just came up with that. But you guys know what I'm saying by now. What we do is we look at things such as we look at populations, we look at samples, we look at observations, and from that we can describe what we see by using simple equations, right? Such as the equation to give you a mean, the equation and the formula to give you a standard deviation. So based on those 2 formulas, which you already know, the formula for a mean and the standard deviation, it gives us a little bit more of a description over what we're looking at. The average time it takes me to drive to work, the average bill or the average extra bill that I pay for on my cellular plan. And then the standard deviation is the spread around the mean. And the larger the spread, the more variation there are. So you guys know how to do that. The empirical rule is a mathematical rule based on that. It's based on a mean, and it's based on a standard deviation. But it's the first mathematical law that I'm going to show you and illustrate to you that has to do with putting together predictive models. Now, that's a big buzzword. It really is. If you work in the insurance industry, as a professional, you put together predictive models, right? You need to predict what the insurance risk is and then determine what the rate is, right? Depending on a bunch of different things. If you work in healthcare, you work with predictive modeling. You think about it. If you work with just about anything, you deal with predictive modeling. I did a project recently for Exelon. If you're familiar with Exelon, they're the energy company here in the Chicago area. And we were doing predictive models to predict energy usage for certain neighborhoods on certain scenarios for certain years. So if you have a background in predictive modeling, you're probably doing okay financially, because this is something that everyone can do. It really is not, but it's not hard. And this is where you're going to start really doing this. And keeping with my mantra of this stuff, or mantra, I don't know how you pronounce that. I'm trying to teach you math, by example. You always hear that. You're going to learn by example. And example base, I don't know what that means really, but I'm trying to give you context to this rather than just showing you numbers and having you parrot them back to me and like to memorize them. That doesn't really show me that you know this, and it probably shouldn't show you, and it certainly wouldn't show an employer that you know this. But I want you to be able to put together, your own brain, like my grandmother said. Use the brain that God gave you. That's like the best advice I've ever heard. It really is, and that's for free, by the way. My grandma didn't charge me either. All right, so the empirical rule is the first mathematical law that deals with probability. And it has to do with this. If we have a description of past events in English, we have a lot of examples that we work with, right? What have we worked with so far? Let's just say we have a sample of 100 times I drove into work. Based on the results of those samples, or based on those observations, we can make predictions on new ones. Okay, sounds right, makes sense. That's using what's called the empirical rule. For example, let's just say we're measuring how long it takes me to drive to work. That seems to be an example I'd like to use. So we'll stick with that. So work and school are the same thing for me. So if it takes me 18 minutes to drive to work one day, next day it takes me 19 minutes. Next day it takes me 17. Don't write them down. That's okay. Next day it takes me 17. Next day it takes me 18. Next day it takes me 19, right? So right now what you're doing is your mind is kind of like absorbing them. And if I asked you right now to give me a mean and a standard deviation of those numbers, don't worry, you don't need to write them down. You'd be able to do it. You'd say, okay, well, based on that, I got the formula for a mean, and I'm making this up. The mean would be 18.2 minutes with a standard deviation of 1 minute and 30 seconds. You would be able to do that. I've shown you how to do that. Okay, so that's descriptive math. Now let's do predictive math. So let me just expand that and just kind of make the problem a little bit different. So I'm not asking you to describe something, but I hit you with something like this. I'm like, all right, Mr. and Mrs. Smarty Pants. So the mean is 18.2 minutes, right? Tomorrow, give me your prediction percentage-wise. If Bob is going to be, how about this? If Bob's going to take 19 minutes to get to work, you should be able to start thinking about that and say, well, you know what? Bob, you're right. If I got all this data on the past events, I should be able to make a prediction on the future one. Albert Einstein had a real good quote. I quote him a lot because he was smart, not because he did things such as nuclear physics, but he was smart because he couldn't do simple things. Albert Einstein rarely drove a car because he thought it was too complicated. And one of the things Albert Einstein said is the future is just a past event that hasn't occurred yet. And I love that. Think about that for 1 second. The future is just a past event that hasn't occurred yet. That's absolutely true. Think about it. So right now, if I said tomorrow it takes me 19 minutes to get to work, we don't know if that's true or not because it's not tomorrow, right? But if it was the day after tomorrow, it would have been a past event and we would be able to measure it, right? It's kind of deep, isn't it? So tomorrow it takes me 19 minutes to get to work. We don't know if it takes me 19 minutes to get to work or if it doesn't take me 19 minutes to get to work. That's called a prediction. Okay, so it's a predicted value. 19 hasn't happened yet. But guess what? 2 days from now, it has happened. So we could actually look at our formula or our equation that we did 2 days ago and look if it was right or not. Think about how that works. This is done in financial markets all the time. A different lecture. I have some experience with that on the math end of it. I do not have a finance background, but I got a math background. Let's just say we look at the close price for a stock. So we got Bob's, bell bottoms, and beta. And we look at the close price. It's an equity. It's traded on the NYSE, right? Could happen. So we look at the close price for the past 30 days, the past 300 days. Hey, heck, the past 3,000 days. We can look at it, right? Now, what can we do with those numbers? You already know how to do this. You can give me a mean, and you could give me a standard deviation. You could say the mean closing price for Bob's, bell bottom, and beta is $50, let's just say, with a standard deviation of 25 cents. I could say, okay, with that, what is your prediction for where Bob's, bell bottom, and beta is going to close tomorrow? You would say, I don't know, Bob, because it's not tomorrow, but you could give me a prediction based on the data you already have, right? You can. That is called a predictive model. Now, there's different ways that we can make predictions, and there's different equations that we can do or use to make those predictions, and different mathematical laws that we can use that support that. So, again, I'm selling you on the big picture here still. Remember I told you when I started that this is going to be dense? Notice I haven't changed the slide yet. You're still looking at this, right? Because this is not stuff they're graded by the pound. You're graded like by the gram on this stuff. So let's talk about the empirical rule. The empirical rule states a few things. The first thing it does is it looks at a standard deviation. And you see that here on kind of like, I'm going to put my cursor here. I'm pointing to it, but you don't see it. But you see like where it says -3, -2, -1, 0, 1, 2, 3. This is the distance from the mean. The mean is right in the middle, right here. This is the mean. Now, I'm only showing you part of it, so just bear with me, because it's kind of a chicken and an egg thing, and I can't show you one thing without showing you something else. So I'm a little bit of a disadvantage here, so bear with me. So the mean would be in the middle. So the mean just says, if this is the mean, whatever this is here, 50%, and you already know this, of my observations are going to be less than the mean, right? And 50% of my observations, or my values for my observations, are going to be above the mean. Remember, the mean is an average. So that should make sense to you, that if we have a mean, whatever the mean is, that 50%, if you add 34.1, 13.6, 2.1, and 0.15, this equals 50%. So 50% of my values are above average, right? 50% of my values are below average. Makes sense. Another quote from Albert Einstein. Love this one. Half the people you meet today are below average, right? Mathematically, that's absolutely true. Half the people you meet today are below average. Half the people you meet today are above average. Now, I guess we could debate on below average of what and above average of what, but mathematically, that's a truth. Half of everything is below something, half of everything is above it. That's what an average is. So look at these other numbers here. We got 0, 1, 2, and 3. These are deviations from the mean. These are deviations above the mean, going to the right, and going to the left, we have deviations below the mean. Now, you already know how to compute a standard deviation. And remember, standard deviations by themselves don't really say much. It's kind of like, well, it says like half the picture. I mean, it would be like, if I asked you a question, what color do you want to paint in your room? You would say, well, what color do you want? It's kind of a paradox, a standard deviation. A standard deviation by itself, without any context, is kind of what's called a dimensionless number, which means it has no context. So since standard deviations are dimensionless, this is where I'm giving them context here. So this is what the empirical rule says. The empirical rule says that, and these numbers are constant. I didn't compute these numbers. I didn't compute them. They're part of the empirical rule. Notice I haven't put any data in here. Basically, the empirical rule says that 68.3% of all observations, 68.3% of all observations are going to be within one standard deviation of the mean. Why? Because it's a mathematical law. It's a mathematical law. The speed of light is a mathematical law. Pi is a mathematical law. Dividing by 0 is a mathematical law. It's a law. 68.3% of observations will in a perfectly distributed curve. A little more on that later. Again, I'm kind of using the 90-10 rule. I'm fudging a little bit just to sell you on the big picture, okay? Keep that in mind. But the empirical rule says that 68.3% of all observations, right, will be within one standard deviation of the mean. This is why standard deviation measurement for descriptive statistics is so important. The empirical rule is also a mathematical law that says that 95.4% of all observations will be within 2 standard deviations of the mean. It also says that 99.7% of observations will be in 3 standard deviations. Now, these numbers that you see here, these percentages, are just numbers that show you like 34.1%. Remember, this is just divided by 2. So it's like 68.3 is between one standard deviation. These percentages just divide that by 2 and says 34% will be one standard deviation below the mean, 30% will be above. Now, this 13.6 just means that 13.6 observations will be between one standard deviation to 2 standard deviations above the mean. 2.1% will be between 2 standard deviations and 3 standard deviations above the mean, and a small, very small, 0.15% will be more than 3 standard deviations above the mean. Now, ditto with below the mean, and that's why you get this 68%, 95.4%, and 99.7%. Now, this is the time where you look at this and you stare at this graph and you stare at what's going on, not till your face falls off, but like right before your face falls off, because that's kind of dense. But what I did here is I made it easy. Well, sort of easy. What I did is I used an example to kind of illustrate this. So let me change my slide. Let us take our man Brad here, and let's put in some data. Now, for Brad, we have a bunch of observations that you see here: 10, 12, 23, 23, 16, 23, 21, and 16. So let's put some context here. Let's just say this is the time it takes Brad to drive to school, right? Me and Brad drive together. So Brad and I drive to school, and we measure how long it takes us to get to school. Now, we have 8 observations. Could be 80, could be 800. In my world, it's 8 million or 800 million. So we could get 2 descriptive numbers here for descriptive math. We could get a mean, right? That's the bottom where we got me, right? Or mu, it's me, but okay, is 18. So on average, the mean time it takes Brad to drive to school is 18 minutes. And also, we have a standard deviation of 4.89. I'm going to round it. Let's call it 4.9 for the sake of not looking at all these ugly numbers. So you already know how to compute a mean. You already know how to do a standard deviation. If you don't, you need to stop now and you need to go back and figure that out, because you can't go any further until you figure out the formula for mean and standard deviation. Now, that's what I was telling you before. All this stuff really builds on each other. Remember I told you, or I mentioned, that just everything that we do in the world is addition, subtraction, multiplication, and division. Everything is based on those 4 things that we do in arithmetic. And, when we don't learn arithmetic, we can't go on from there. We can't learn anything else until we can add, subtract, divide, and multiply. I mean, that's why we do that in school first, probably because we can't do anything more complicated, but that's up for debate. It's the same thing when we're adults here. Sometimes we want to skip through this. Like, no, I'm better than this and I should be in the advanced math class. No, you're not doing yourselves any favor. Seriously. If you can't do the standard deviation or the mean, go back and figure it out. And if you need help, reach out to me. I'll get you up to speed. All this stuff builds on each other. Nothing will make sense until you get the step before it. And that's what you're looking at here. So anyway, so we got Brad. That's got Brad and me. We go to work, and it takes us 18 minutes on the average to get to work with a standard deviation of 4.9 minutes. And that's just rounded up. So let's put those numbers and plug them into the empirical rule. Notice I'm not giving you an equation yet. I'm not going to. So let's put those numbers in. Now this graph is the same. Now let's put the numbers in. Now notice 0. 0 is the mean. The mean is 18. So go to the right. So with if you need to see the standard deviation, again, you could go to the slide before, but it's 4.9 and the mean of 18. I don't have it here, but go back to the other slide. You'll see it. So 18 is the mean. So that's on the top. Now the empirical rule says that 50% of all of our observations are going to be above average and 50% are going to be below average, right? You're rolling your eyes saying, Bob, that is the easiest thing ever. Believe it or not, that's the starting point for the empirical rule. Now we just get a little bit more detailed. So you already kind of know it because you're like, yeah, you're right. I mean, half the people you meet are below average. Half the time I drive to work, it's below average. Half of the measurements are going to be above average. That's what the average is. The empirical rule will say, right on, dude, do that, you got it. But the empirical rule also says that 68.3% of our observations, or the values of our observations, are going to be within one standard deviation. Now, this is where the deviation is important. What is a deviation? 4.9. And I just did the liberty here of taking 18. One standard deviation below the mean is 13.1 minutes. One standard deviation above the mean is 22.9 minutes. Why? Think about it. You already have the number. What's the standard deviation? Bueller. Anyone? Anyone see Ferris Bueller's Day Off? If you're like under the age of 40, you probably don't know what I did. Rent it this weekend. Go to Redbox, or Redbox is still a thing, right? So anyway, so one standard deviation from the mean is 22.9 above the mean, and one standard deviation below the mean is 13.1 minutes. The empirical rule also says that 95.4% of the values of my observations will be within 2 standard deviations of the mean. And I took the liberty to plug those numbers in, and that would be 8.2 minutes is 2 standard deviations below the mean, 4.9 plus 4.9, right? Or 18 minus 4.9 minus 4.9 equals 8.2. And to the right, you see 27.8. So 27 minutes or 27.8 minutes. I almost said 27. Well, 27.8 minutes is 2 standard deviations above the mean, or between the mean and 2 standard deviations above. So basically, in English, that if we have a value between 8.2 minutes and 27.8 minutes, basically 95.4% of our values will fall in that range. We also have the empirical rule telling us that if we look at 3 deviations from our mean, that we only have 2.1. Again, 2.1 of our values are going to be between 2 standard deviations and 3 standard deviations above the mean. And looking to the left, 2.1 is between 2 and 3 standard deviations below our mean. And again, if you look down at the bottom number, we have 99.7. And that tells us, the empirical rule tells us, that 99.7% of our values are going to be between 3.3 minutes, and 32.7 minutes, right? So 99.7% of our observations are going to be between 3.3 minutes and 32.7. This is the empirical rule. It has to do with distribution. It has to do with central tendency. This is it. Now, again, this is where you stare at this, and rather than nodding your head and going, stop the video a little bit, stop taking notes, and just go back and start looking at the numbers and just start it making sense to you. Now, here's the thing with this. When your brain starts learning things, your brain is growing. Okay, now, not all growth happens instantaneously. This is why I always say that, you can teach a monkey to memorize something. You can teach a fish to play a video game. Memorizing things is not learning them. Your brain grows when it learns. Do any of you work out? I don't work out, but people that work out will tell you you can't gain a bunch of muscle mass by working your ass off in a week, or you can't lose mass or lose weight by exercising. And, I'm just going to take all week and I'm going to exercise my ass off and I'm just going to lose 50 pounds. It doesn't work that way. Okay. Learning is like that too. So you need to take this in small doses. And if you looked at this 15 minutes today, 15 minutes tomorrow, 15 minutes the next day, it's a lot better than just saying, I'm just going to, over Sunday, I'm going to buckle down and I'm going to learn this. No, you're not. No, just like you're not going to be able to gain muscle mass in one day or lose weight in one day. And if you're wrestling, I guess you could, sweat and lose some water weight. But you guys get my point here. Again, I'm trying to explain to you how to learn this. It's like, for example, I'm an amateur musician and I'm trying to learn how to play the cello. And it's a little bit tough for me because I need to practice it. And I'm realizing that I just can't buckle down and double up on my practices. I can't say, I'm not going to practice today or tomorrow, but on Saturday, I'm going to practice for 8 hours straight. That doesn't do anything for me. As a matter of fact, that kind of makes me worse sometimes because I lose form and my hands get tired and my arms get tired. Your brain will get tired if you look at this stuff and try to do this for 8 hours a day. So just know, not just for this class, but just in general, that memorization is easy, but learning things takes time. So if you don't get this by the end of class today, and if you need to spend more time on it, you're paying attention. That's exactly how it's supposed to work. There's no shortcuts, trust me. Look at it, practice it, and try to get more. Sounds like I'm wrapping things up, and I guess I kind of am. But anyway, so get back on track here. So the empirical rule is a mathematical law that says that 99.7% of all of our observations are between 3.3 minutes and 32.7. All right, so what? So anyway, notice what we've done so far is we've just looked at descriptions. I mean, these are just observations, but we could take this one step further and use the empirical rule and develop what's called a z-score. The z-score is the first formula, and I'm not showing you yet, that has to do with prediction. And let me just explain how this works. Let's just say, and I'm gonna leave you with one example. I'll leave you 3 examples. Let's just say that someone comes to you right now and says, hey, what are the odds that Brad and Bob take 33 minutes to get to school tomorrow? You can use what you learned today to start thinking about that predictive model. You don't have the equation yet. I'm not going to show it to you yet. But you could look at this and say, well, the empirical rule tells us, I'm speaking academically, you don't talk like this in real life, but you could say the empirical rule tells us that the mean time that takes Bob and Brad to get to school is 18 minutes, because we've measured it, with a standard deviation of 4.9 minutes. So 3 standard deviations above our mean would be 32.7 minutes. So in general terms, what would be the odds, in general terms, that it would take Brad and Bob 33 minutes to get to work tomorrow? In general terms, you would say that's extremely unlikely. And you could use the empirical rule to back you up. You could say, well, based on past performance or past measurements, past metrics, past events, fill in your blank there, that 32.7 is 3 standard deviations above the mean. So 33 is more than 3 standard deviations above the mean. And if you take a look at this, only 0.15 of observations are going to fall above this. So you could say it's extremely unlikely. Or I could say this. I could say, what are the odds that Brad and Bob take 13.1 minutes to get to work tomorrow? You can look at this and look at the empirical rule and say, well, 33.1 is one standard deviation below the mean, right? 13.1 minutes is one standard deviation below 18. And if you look in the shadow part there, 34.1% of the observations fall within 1 to 2 between 0 and 1 standard deviations from the mean. Again, we're speaking in general terms. You would say it's very likely, or you could say there's the probability of that happening are 30. I won't give you a number because I don't want to confuse you. But I'm still selling you on the big picture. You can use the empirical rule to make predictions. You can. Now, when you use the empirical rule to make predictions, there is a formula called a z-score that'll give you the exact percentage. Right now, I just gave you general ideas, right? I'm just like, all right, well, if it takes Bob and Brad 33 minutes to get to work, you look at your empirical rule and you're like, that's extremely unlikely. And there's less than a 0.15% chance of that happening. But the z-score will tell you exactly where that prediction would fall here. So you would be able to say something like, based on the past events or based on past measurements, the odds of Brad and Bob taking 33 minutes to get to school tomorrow are 0.09% or extremely unlikely. When is this important? Work in financial markets. This is very important. Look at the close prices. Look at the dividends. Look at any sort of measurements for any equity. Or if you're doing bonds, look for the yield, and look for all those metrics. Measure them, and then based on those measurements, you could plug numbers in, let's just say these are closing prices for Bob's, bell bottoms, and beta. All right, okay, the mean close price is $18 with a standard deviation of $4.90. All right. So based on that, if you're doing like a portfolio of not just Bob's, bell bottoms, and beta, but 20 or 30 different equities, you can use simple descriptive or predictive tools like this to run a lot of what-if scenarios. Like, what are the odds that Bob's, bell bottoms, and beta closes at X price tomorrow or X minus price tomorrow? You can use the empirical rule and z-scoring to put together, albeit they're simple, but you're on your way. You're on your way to look at these real life things around you and making predictions based on measurements, dozens of measurements, thousands of measurements, or millions of measurements. You could use this for the Center for Disease Control, look at COVID spread. Something I know a little bit about, more on that later, where we can look at past events and we look at measurements and we could put in z-scores on the probability of a certain population of getting COVID in the next X amount of days, based on demographic or location, gender, ethnicity, name it. We could put together probability models based on the empirical rule and z-scoring. So that's all I have for you today. Notice I didn't show you the formula for z-scoring because I want you to absorb this. I want you to wait a day, think about what I just said, go through any sort of other reading that you have, learn more about this. You should have your resources available to do so. If not, reach out to me. Start looking at examples. And if I was just learning this and I were you, I would look at this example I gave you because just about everything that you need to know is on these slides. Like with, the example of like the real numbers and especially the graphic for the empirical rule. So that's all I have for you today, gents and gentites, gentlemen, ladies and gentlemen, right? Is it still politically correct to call each other ladies and gentlemen? Hope I didn't offend anybody. I didn't mean to. You guys know me. I offend everybody and nobody at the same time. All right, so I wish you all a very well rest of the day. Be safe, be happy, be healthy. help each other. And if you have any questions, please reach out to me. The next lecture we're going to have is going to be talking about z-scoring. And before you can understand z-scoring, you need to understand this. So have a great day. Thank you. Bye-bye.